Calculate the wavelength of the emission. This is again from Bohr's theory. Spectrum. Emission transition, if it starts from orbit, okay, having a radius, R initial is 1.3225 nanometers, okay, and as it falls, final radius is 211.6 picometer. Oh my God. Name the series to which this transition belongs and the region of the spectrum. We are assuming this to be hydrogen atom. It seems nothing else has been mentioned. We are shameless enough to assume this as hydrogen. What do we do? Well, we are given radii. Yes. And what does radius have to do with any other data? Can we have some idea, some inkling? Yes, electron can revolve only in those orbits for which circumference is integer multiple of lambda. I mean, we could use that in case you feel like. Otherwise, we can simply say that using the radii, we can calculate. Once we are aware of this is the radius, we can calculate n, this is the value of n, and accordingly we could get the transition. R is R naught n square by z, and since z we are assuming as 1, R by R naught is n square. So what R initial? What is R initial? It is 1.3225, okay, by R naught. R naught is 0.53 angstrom unit, or 0.0529 nanometers for hydrogen atom. 0.529 angstrom units is radius of first Bohr orbit. We use that. How much does that come out to be? Well, looks like 4. If I just multiply 0.53 by 4, 4 is at 12, 21. No, not really. So, that 4 doesn't look like a good number. Let's try 5. 5 is a 15. 5 is 20, 20. Yeah. So, this looks like 25, which is also equal to n square. And n initial is root 25, which is 5. This gives me that the electron was initially present in n is equal to 5. Wow. That's convenient. That's cool actually. Similarly, R final by R naught. And how much is that? It's so many picometers, 2.116. 2.116 angstrom units divided by 0.53 angstrom units, which is R naught. Now what I see is 5 4s are 20. This looks like 4, which is n final square. Therefore, n final looks like 2. Wow. So from fifth shell, electron is actually falling to second shell. This is Balmer transition. If it is Balmer transition, which is the spectrum? This is the visible region. How do I know this? Electrons from anywhere, if they fall in n is equal to 2, they represent Balmer series, and Balmer series very well lies in the visible spectrum, right? So, the series to which this transition belongs, we don't have to calculate anything else anyways. The moment I see n is equal to 2, it is Balmer series, and that ends it. There we are. Oh no, we also had the wavelength. Let's calculate wavelength. That's not very difficult. How do I get that? 1 by lambda is RH, 1 by 2 square minus 1 by 5 square. We use Rydberg's formula, and RH is 1.097 into 10 raised to 7 per meter. 1.09 into 10 raised per meter. Can we do that? Of course, nobody can stop us. This is 1 by 4 minus 1 by 25. 25 minus 4, 21 by 4 into 25. That's lovely. As lovely as it gets. Therefore, lambda is 100 by 21 into 1.09 into 10 is to minus 7 meters. Lovely. Solve that. That comes out to be 434 nanometer, or roughly 4,300 angstrom units, which is Balmer region or visible region very obviously.